Hello class, this is chapter 2 part 1. This chapter is going to be divided up into 4 parts, which you can see here. This video is over 2.1, just basic chemistry. The whole chapter is on chemistry, but let's get started. So some of this beginning stuff will just be definitions. So matter is anything that has mass and takes up space. Matter exists in 3 major states, but also plasma. But you know these: solid, liquid, and gas. Y'all been taught that since grade school. Element is something, substance is the biology word for something. That cannot be broken down into something else. And it's typically composed of only one type of atom. And atoms are the smallest thing that can have the properties of an element. And they are basic building blocks for matter. And your body is made up of 4 major atoms. These top 4 right here: carbon, hydrogen, nitrogen, and oxygen. So know those top 4. And that should be good. We're weird. A lot of the carbon, nitrogen, even most of the oxygen is locked up in organisms, things that are alive, whereas a lot of the rest of these elements, they're more common in the non-living parts of our environment, soil and rock and stuff like that. Although it is debatable that whether soil is alive or not, but I'm just talking about the particulate part of soil. So again, an atom is the smallest thing that has the properties of an element. They are the building blocks for matter, but they also have their own building blocks, these 3 right here: protons, neutrons, and electrons. Protons are positively charged. They have mass. Because they have mass, they're in the nucleus. Neutrons are neutral. They have no charge. They also have mass and therefore are also in the nucleus. So while they have mass, they don't contribute any charge. Electrons are negative, and there's no alliteration there, so you'll just have to remember that neutrons have no charge and electrons are negative. Electrons have very little mass. They weigh so little that we don't care about, and that's what negligible means. They do have some mass, but it's so small compared to the protons and neutrons, and these are already tiny particles, so we don't really care about it. The electrons orbit the nucleus, but it's not a fixed orbit like the planetary orbits, like Earth, Saturn, Mars. It's a little more random as to where they will be, but they do, travel around the nucleus. And the reason they stay close to the nucleus is because the negative charge of the electrons is attracted to the positive charge of the protons. So the electrons, while they have some freedom, they won't get too far because of that attraction. And just remember, in chemistry and physics, opposites attract. So here they're showing you a couple models of atoms. It's 2 models of the same atom, which I believe, that is helium. which is the stuff that makes your voice go squeaky if you inhale it. It has 2 protons, 2 neutrons, and 2 electrons. And the protons and neutrons are in the nucleus, which you'll learn 2 different definitions of the word nucleus in this class, and there's another nucleus in neurology. So try to keep these separate. The nucleus in an atom is centralized, and it contains the protons and neutrons. So it contains the mass of the atom, because remember, those are the particles that have mass. The electrons are somewhere out orbiting the nucleus. They typically have somewhat of a set pattern, and we call those orbits a shell, an electron shell. We're about to look at the periodic table. I want you to know what the atomic number tells you and how the atomic mass and mass number can be useful. So in our periodic table squares, you're going to have a number in the top, you're going to have a symbol, and then you're going to have a number on the bottom. The symbol is representative of the name of the atom or the name of the element. And most of them or quite a few of them are easy, like C for carbon, H for hydrogen, but some of them are based on their Latin names. So natrium is the Latin name for sodium. So that doesn't have alliteration. That's just something you have to learn through usage. On the periodic table that I plan on giving you, it will have the name present. Or I'll ask you a multiple choice question where I give you the information you need to know, like the name, the atomic number, and the atomic mass. So the atomic number is this number at the top. Sometimes it's in the middle, sometimes it's off to the side, but it will be towards the top of the little square. But that tells you the number of protons in your element, and if you're talking about sort of your standard atom, it also tells you the number of electrons, because remember, protons are positively charged, electrons are negatively charged, and because of that, opposites attract. And so in general, these atoms are balanced, so the number of protons equals the number of electrons. So that atomic number will always tell you the number of protons. It also often tells you the number of electrons. If you see something with a plus sign or a minus sign, then there's a difference, there's an imbalance somewhere, and I'll talk about that a little bit more later. But in general, if we just write an atom, the number of protons equals the number of electrons. So that atomic number tells you both. The mass number we typically don't see. We usually see the atomic mass on a periodic table. And the atomic mass is the bottom number. It's usually centered, but it can also be in a different spot. But you can tell it because it has all these decimal places. And when we use the atomic mass, we're going to round that. So I would round 12.011 to 12. And in fact, the mass number for carbon is 12. How we're going to use the atomic mass is to find out the number of neutrons. And the way you find the number of neutrons is by subtracting the atomic number from the atomic mass. And that is because the atomic mass is essentially the number of protons plus the number of neutrons. And since the atomic number is the number of protons, if we subtract the two, we get the number of neutrons. So it is the atomic mass, or mass number, minus the atomic number. So be able to, if I give you an atomic number and an atomic mass, be able to tell me the number of protons, the number of electrons, and the number of neutrons. And so here they flipped it to what I showed you, but again, if I give you a periodic table, it'll be more like what I showed you. I'll go over that in a second. Alright, so the proton number is what makes an atom unique. What makes an atom of a certain element. So carbon has 6 protons. If you change the proton number, it becomes either nitrogen, or I forget what happens if you go the other way. But it becomes a different element. And so the proton number is what makes each element unique, an atom of each element unique. We can change the number of neutrons, we can change the number of electrons, and it remains an atom of that element. When you change the number of neutrons, you change the mass. But there's still atoms of the same element. So here we have 3 different atoms of carbon. But they have different masses. And they're named by their mass number, their mass. And that means they have a different number of neutrons. So carbon, 12 minus 6 gives you 6. So sort of your normal standard carbon atom has 6 neutrons. Carbon 13, 13 minus 6 gives you 7. So carbon 13 has 7 neutrons. Carbon 14, 14 minus 6 is 8. So carbon 14 has 8 neutrons. So know the definition. Isotopes are atoms of the same element that have different numbers of neutrons, which means they have different atomic masses. Some isotopes are radioactive. Radioactivity can be harmful, but when we use them in the science field, in the medical field, they're often really helpful. So some isotopes are radioactive, some are not. Some radioactive isotopes are harmful, but some are not. So when I was doing research, I worked with a couple of different isotopes. I worked with tritium, which was a hydrogen isotope, and P32. Actually, I didn't work with it, but I got training on it. P32 is a phosphorus isotope. They're both radioactive. They both spontaneously decay. But the training for tritium was basically don't eat it. But I didn't need gloves. Well, I use gloves, but you didn't need gloves. You didn't need eye protection. You didn't need an apron. You didn't need a shield or anything like that. However, the P32, you had to have a shield, an apron, goggles, gloves, respirator, all that stuff. Different isotopes, or different radioactive isotopes, give off different types of radiation, and some does not hurt us. It moves very slow. It has low intensity, and it's not destructive. But some does move very fast. It's very intense. It has short wavelength, and it is destructive. But the reason we care about isotopes is because we can use them. Everyone's pretty much familiar with carbon dating. All these things decay at a predictable rate, so we can use them for carbon dating. Because they give off energy, we can use them in medical imaging, so we use them for like CAT scans. One of the tricks they do to find cancers, to find tumors, they'll feed you glucose that has a little bit of a radioactive isotope, what's known as radiolabeling, and then that glucose will go all over the body, but tumors tend to hoard glucose because they're very metabolically active. So when you do a CAT scan or image them, then they glow on the CAT scan because they're giving off this radioactivity. So isotopes are really useful. Know their definition. Know that some are radioactive and some are useful. Okay, so when we talk about atoms reacting, because they have to react in order to form bonds, they have to form bonds in order to make matter. So things like matter makes up your cell phones, it makes up our bodies, all that stuff is made out of atoms. So we like knowing how things work as scientists. So atoms, we like to be able to predict which atoms are going to go together and how strong their bond is going to be and things like that. So I'm going to get to all of this. We're going to look at a bunch of atoms. So here in these Bohr models, they're showing you the nucleus just as a sphere, a colored sphere with the atomic symbol on there. So H is hydrogen, C is carbon, P is phosphorus, N is nitrogen. If sodium was here, it'd be big N, little a. And then they're showing the electron shells. Remember I said the electrons surround the nucleus, they orbit the nucleus. Each orbit is somewhat predictable, and each orbit is called an electron shell. The outermost shell, so this one for hydrogen, this one, that second one for carbon, the third one for phosphorus, whichever one is the outermost shell, that is known as the valence shell. Atoms want complete valence shells. If their valence shells are not complete, atoms are not happy, and they will look to complete their shell by interacting with other atoms. So if I ask you, is this atom radioactive? All you need to know is how many electrons are in its valence shell. I may tell you how many electrons are in its valence shell, but more than likely I will tell you either its atomic number or the number of electrons it has. So this innermost shell, the valence one for hydrogen, it is complete with 2 electrons. So you can see 2 here, you can see 2 here, and all of them, all 6. So that innermost shell is complete with 2 atoms. All the others, as far as we care, the second shell, the third shell, even the fourth, is full with 8 electrons. Those 2 facts, the first shell is full with 2, the second shell, third, and so on, is full with 8. That is known as the octet rule. And so if I give you a mystery atom and I tell you it has 10 electrons, you know to go on that first shell, and 8 go on the second. It has 10 total, 2 go on the first, 10 minus 2 is 8. So 8 goes on the second shell, and because its valence shell, its outermost shell, is complete due to the octet rule, it has 8, then it's not reactive. All these others, carbon has 4, nitrogen has 5, oxygen has 6 in its valence shell, phosphorus has 5 also, and sulfur has 6 also. But something like chlorine would have 7 in its valence shell. All those are reactive because their valence shell is not complete. Earlier we looked at helium. Helium had only 2 electrons, but that fills up the first shell. So that satisfies the octet rule, and helium is not reactive. So be able to tell me if an atom is reactive or not. And then I also want you to be able to tell me how many electrons are in its valence shell. And you might want to do a little drawing like I did. Or I will show you a trick. So here's a periodic table, and I'm going to go from some of the information from the slides I skipped. Your periodic table is organized into rows. And columns. Now, the rows are called periods. And each period, or the period number, I should say, tells you the number of electron shells. So hydrogen is in period 1. It has 1 electron shell. Carbon, right here, is in period 2. So it has 2 electron shells. Phosphorus, I think we looked at that one on the previous slide. It's in period 3, so it has 3 electron shells. The column is called a group. And the group number tells you the number of valence electrons. So hydrogen is in group 1. It has 1 valence electron. Now, I just want you to look at the tall columns. This is where most of the atoms in biology come from anyway. What I mean by tall is that it has columns taller than this line. So it has atoms in period 1, 2, or 3. Those are the columns I want you to know. On this periodic table, it is numbered for you with Roman numerals, but it is the A groups. Notice these are B groups. So we just want to pay attention to the A groups. Those are where the atoms that I ask you about are going to come from anyway. But they skip all this mess in the middle. So this is group 1, this is group 2, this is group 3, 4, 5, 6, 7, and 8. So carbon is in group 4. It has 4 valence electrons. Phosphorus and nitrogen are in group 5. They have 5 valence electrons. Oxygen and sulfur are in group 6. They have 6 valence electrons. I talked about chlorine because it had 7 valence electrons, and look, it's in group 7. And then our mystery atom was neon. Look, it has 10 total electrons, and it is in group 8. So that's the periodic table. Another thing I want to talk about as atoms, as you go from left to right, atoms become more electronegative. Atoms of these elements become more electronegative. And that means they're greedy for electrons. So they like to hoard electrons. They attract electrons very strongly. So hydrogen is not electronegative. Something like oxygen or chlorine is highly electronegative. They are very greedy. Sulfur too. And then my last little note, all of these atoms in group 8 are known as the noble gases. For one thing, they're gases. For another, they are noble, they are stuck up, and they don't socialize with anybody. They don't form bonds with anyone. They're non-reactive. So that's why we call them the noble gases. So remember, if its valence shell is full, due to the octet rule, 2 electrons on the first, 8 on the second, third, fourth. If they're full, they're non-reactive. If their valence shell is not full, then they are reactive, and they will form bonds. So our next section will be on bonds, part 2, and then we'll move into water and pH.